right, so we're going to start talking about a derivative. And so what I kind of need to bring up is the rates of change and tangent lines, because what a derivative is it's the slope of every tangent line you can make across a function. So there's two different kinds of lines that we can talk about. We have tangent lines and secant lines. So normally, if we have a linear function and you want to find the slope between any 2 points on it, that could be considered a secant line. What if I have like a quadratic? I can pick 2 points here. I can find the slope between those 2 points, and that is a secant line. Right, a tangent line would be right up next to it, where it only is going to touch at one, usually going to only touch at one point. You know, sometimes maybe this tangent line here, maybe it might technically cross twice, but we're only looking for a specific rate of change there. So we know what slope is, and we know the slope between any 2 points. So that's this average rate of change, right? It's a y value minus a y value over an x minus an x. Okay, same thing as secant line. Now the instantaneous rate of change is that tangent line slope. So kind of like I was drawing here, I'll go back to that quadratic example. You know, if I want the slope here, if I do a normal slope between 2 points, well, I only have 1 point. So the slope I'm going to get is 0 over 0. And that doesn't tell me anything. We haven't moved anywhere. So what we want to do is take a limit as that change in x value. You know, we could start off here and get closer and closer and closer to the tangent line. So as that change gets smaller and smaller, we can find what that instantaneous rate of change will be. And then this piece here, anytime we talk about the difference quotient, that is the difference quotient, f of a plus h minus f of a all over h. You might see it as f of x plus h minus f of x all over h. So let's use these two things. So the average rate of change for this function here over the interval 1 to 3. So I just need the 2 points. So I can find f of 1. And let's see, 1 cubed is 1. 1 minus 3 is negative 2. And then I can also substitute in 3. So 3 cubed is 27. 27 minus 9 is 18. Okay, so I can find the slope between those 2 points, right? It's y minus y over x minus x. So I get negative 20 over negative 2 to get a positive 10. And that's my slope, right? Well, let's use the difference quotient and find the slope of this quadratic function at this point. So that difference quotient is this piece right here. But we want to find the slope. So the slope is the limit as h goes to 0 for f of a plus h. So in this case, a is 3 plus h minus f of 3 all over h. So let's do these calculations here. If I substitute in 3 plus h squared, I'll FOIL that out in a minute. Then f of 3 squared is 9 all over h. Let's go ahead and square out that 3 plus h. I'm going to write it over here. 3 plus h times 3 plus h. We'll get 9. And then 3h plus 3h, so 6h. And then plus h squared, bringing over that minus 9 we have, all over h. And I'm forgetting my limits here. The limit as h goes to 0. If I do a direct substitution, I'm going to get a denominator of 0, and I don't want that. So let's do some simplifying. I can cancel those out. And I got 6h plus h squared all over h. And if you notice, each of these terms has an h in it. Let me highlight that little h down here. Okay, well, they all have an h. What about now? There we go. Okay, so I can factor it out, and I'm left with the limit as h goes to 0 of 6 plus h. I can plug in 0 now for h and get 6 plus 0, which is 6. So that is my slope at that point. All right, and finding all of that helps us to find the equation of that tangent line. So, okay, this part says write the equation of a tangent line. Same function I just used in that same point. So all we need to make the equation of a line is a slope and a point, because we can use the point slope form of a line here. So y equals the slope I just found was 6 from above, and then x minus the x value plus the y value. And then if you want to distribute the 6 and combine some like terms, you can. But we can leave it like this. I'll say, or we got y equals 6x minus 18 plus 9, which gives y equals 6x minus 9. Okay, so what if a slope doesn't exist? So let's say we find the limit and we get either of the infinities. Then what we have is a vertical tangent line. So then our equation will become whatever the x value is, x equals a, will be the vertical tangent line. All right, there's something called the normal line. This is perpendicular to the tangent line at that point. So once we find the slope, remember perpendicular, we can find the opposite reciprocal for the slope. So I use the limit definition to compute the slope of a tangent line at x equals a. So, okay, let's use that limit definition. The limit as h goes to 0 of f of a plus h minus f of a all over h. So in this case, we have the limit as h goes to 0 of 1 over a plus h plus 3 minus f of a, so 1 over a plus 3 all over h. Now I'm going to want to get all of this into one fraction. So, don't want to forget my limit notation here. All right, so the common denominator here is going to be both of those factors, a plus 3 and a plus h plus 3. That first fraction is missing a factor of a plus 3. And 1 times a plus 3 is a plus 3. Now this second one is missing the factor a plus h plus 3. But I'm subtracting it over. And 1 times a plus h plus 3 is a plus h plus 3. And I'm going to subtract everything over. So minus a minus h minus 3. I'm going to do some simplifying. The a's will cancel. The 3's will cancel. So I'm left with negative h. I'm going to go over here. So I have the limit as h approaches 0 of negative h over, sorry, I can't draw a straight line here, a plus 3 and a plus h plus 3 all over h. And so now I do a thing where I do a fraction over a fraction, and then I do big C over little c. It's the same thing as multiplying by the reciprocal here. So we got the limit as h goes to 0. Big C is negative h times 1. And then little c is h times a plus 3 times a plus h plus 3. The h's will cancel out or simplify down to 1. So I get negative 1 over a plus 3 times a plus h plus 3. Then I can do that direct substitution for a final answer of negative 1 over, and I'd have a plus 3 times a plus 3. So let's just make that a plus 3 squared. So that's the slope at any point A. So, all right, part B says find the slope of the curve at x equals -1. Well, that's the same thing as saying an A equals -1. So if I know my slope is that -1 over A plus 3 squared, I can substitute in -1. So it's going to give me 2 squared is 4. So I have a slope of -1/4. So all right, let's do the tangent line. So our original function was what? 1 over x plus 3. So I probably need a y value to get the full equation. So let's substitute in -1. So 1 over -1 plus 3 is 1/2. So my point is -1, 1/2. And I already know from part B my slope is -1/4. So I can use that. Y equals -1/4 times x minus -1, which will give me x plus 1, and then plus 1/2. You could distribute, combine like terms, all the fun stuff, or I like to just leave it. Now we want the normal line. So if we know the slope of the tangent line is -1/4, the slope of the normal line, and I'm going to use the perpendicular notation here, is the opposite reciprocal. So opposite meaning positive versus negative. So if the original was negative, this new one's going to be positive. And then reciprocal is switching the numerator and denominator. So it's going to be 4. And then we have the same point. So that y value was 1/2. So our new line for our normal line is y equals 4 times x plus 1 plus 1/2. Just needed to change the slope there. All right, use the equation from C to estimate a value. So, okay, y equals -1/4, -1.1 plus 1 plus 1/2. So let's see, we have -1/4. That's going to give me a -1/10, or a -0.1. I'm going to turn it into a fraction just so I don't have to pull out a calculator. So then I'll get 1/40th. And to do like denominators, let's just go ahead and make 1/2 20 out of 40. And so my estimate is going to be 21/40. We can get the decimal for that, but I'm also cool with the fraction. Alrighty. Got a new function here. So given the function f of x is 4x minus x squared, determine how fast the graph is changing at x equals 1. So the question is really asking, what is the slope of the tangent line at x equals 1? So let's first just find the slope of the secant line. So let's find what these are. So f of 1 is going to be 4 times 1 minus 1 squared. So 4 minus 1, so 3. So really we have the point 1, 3. And then we want to plug in this point. This one I might need an actual calculator for. So 4 times 1.001 minus 1.001 squared gives me, and I just did this off to the side in a calculator, 3.001999. So we can find the slope between those 2 points. We can do y value minus y value over x value minus x value. And let's see what we get. To plug that in the calculator. So divide that by 0.001, and I get 1.999. All right, let's find the average rate of change between that first point, which was 1, 3, and then any other point with some h change. So let's see, that 1 plus h, if I substitute that in, is going to give me 4 times 1 plus h minus 1 plus h squared. So let's see, 4 plus 4h, and then 1 plus h squared is going to give me 1 plus 2h plus h squared, but I'm subtracting that over So minus 1 minus 2h minus h squared. Let's combine some like terms. So that's going to give me 3 plus 2h minus h squared. I'll just rewrite that here. 3 plus 2h minus h squared. And so if we want to find the rate of change from there, let's do y. And then minus the y value, so I'm going to subtract all those over. Minus 3 minus 2h plus h squared all over 1. And then minus 1 plus h, so minus 1 minus h. And let's simplify. So 3 minus 3 will cancel, 1 minus 1 will cancel. So I'm left with negative 2h plus h squared all over negative h. I think I can divide each of those terms by negative h to be left with h minus, I don't know why I said h, that should have been 2, sorry, 2 minus h. So what happens to the secant line between the points? Oh, and there's a typo here. We should have this point and this other point here. And 1 plus h, comma, f of 1 plus h. As h goes to 0. So as h goes to 0, that slope gets closer to 2, right? Because it's 2 minus h. And if h is getting closer and closer to 0, the slope is getting closer and closer to 2. So find a general formula for a tangent line between any 2 points. Okay, I'm going to go from a different route that I normally do. I always, between 2 points, do left, right, left, right. But because of what this is going to turn into, I want to do it the normal way that you see. You know, normally this is x1, y1, and this is x2, y2. And we're used to the slope formula being y2 minus y1 over x2 minus x1. Even though that order really doesn't matter, I am going to do it that way. So I have y, which is f of x plus h, minus y, f of x, all over x plus h minus x. And then we can see what this is going to simplify down to, right? F of x plus h minus f of x. X minus x is going to simplify, so I'm going to be left with h, right? So how cool is that? Because doesn't that look like the difference quotient? And then we look at what is happening as h is going to 0, right? We're going to look at a few different notations for the derivative, right? So several different notations, but they all mean the same thing. So you're going to see them used interchangeably throughout the course, whether that be through the textbook or labs or just the way I write it. So we have f with an apostrophe of x. We read that as f prime of x. All of these are for derivative. So you have y with an apostrophe set as y prime. We have dy dx, where we say, it just like I just did, dy dx, or the derivative of y with respect to x. I love that it says awkward to use. It's just a lot to write. I use it when we get into concepts like related rates. I typically am between these two as a personal preference. I just have df dx, so the derivative of f with respect to x, and it could be any function. So it could be g, so dg dx, or dh dx. And again, that will come in handy when we do related rates. And then we also have this notation here where we just have d dx, and then we have a function. So this means, this to me is like the operation. So it's like we're going to take the derivative of this function. Okay. So a couple of these examples might use the different forms, but again, they all mean the same thing. So let's use the limit process of the derivative to find the general formula for dy dx. So dy dx is the limit as h goes to 0 of that f of x plus h minus f of x all over h. So let's substitute it with our formula. So I have the limit as h goes to 0 of f of x plus h. So x 2 times x plus h squared minus 3 times x plus h minus, and then I throw a bracket over functions that have more than just one term so that I remember that I'm subtracting off the entire function. So I have 2x squared minus 3x, and I'll distribute the negative when I go to simplify all over h. All right, let's see what I can try and simplify. So let me distribute some things out. So all over h. X plus h squared is x plus 2xh plus h squared, but I have to distribute that 2 on the outside. So that becomes a 2x and a 4xh and then a 2h squared. Then I need to distribute the 3, so minus 3x minus 3h, and then I'll distribute the negative on that last piece, so minus 2x squared plus 3x. And I bet you I have some things that can cancel. Oh, you probably caught it before I did. That should be an x squared. So 2x squared minus 2x squared minus 3x plus 3x. So I have the limit as h goes to 0 of 4xh plus 2h squared minus 3h all over h. Now again, we should see each of these terms has an h in it. So let's factor it out and simplify. So I'm left with 4x plus 2h minus 3. Then I can do a direct substitution of 0 in, and I'm left with 4x minus 3. So there is the derivative. dy dx is 4x minus 3. All right, let's do it again. So we have y equals x squared minus x. Use the definition of derivative to find f prime of x. So I'm going to go ahead and I'm going to leave the notation as it is. And I'm going to go ahead and just substitute in. So x plus h gets substituted in first. So x plus h squared minus x plus h minus the function as it is. So x squared minus x all over h. Let's do some simplifying or some distributing here. So x squared plus 2xh plus h squared minus x minus h minus x squared plus x. So I have x squared minus x squared, that'll cancel, and then a x, negative x and a positive x. So I get the limit as h approaches 0 of 2xh plus h squared minus h all over h. And then we should be recognizing again that each term has an h, and we can simplify that. So I get 2x plus h minus 1. Then I can do my direct substitution of 0 to get 2x minus 1. So f prime of x is 2x minus 1. All right, alternate form of the derivative, we have still that quotient, right? The limit as h goes to 0 of f of a plus h minus f of a all over h, which is what we've been using so far. Or we can say, hey, the limit as x approaches a of f of x minus f of a all over x minus a. So we can try doing that. So we'll use the alternate form to find f prime of a. So I can use this form Is there another example after that? Yeah, there is. Okay. Or you can use this form and at the end substitute in 1 for a. Either way, it's the same. So let's find f prime of a, the limit as x goes to a, which for us is 1. Plug a 1 in there. So f of x is just the function. So square root of 3x plus 1 minus f of a. So that's me substituting in 1. So it's going to be square root of 4, which gives 2. And then all over x minus a. Well, uh-oh. If I go to evaluate this limit, if I try direct substitution in the denominator, I get 0. And I don't want there to be a 0 there. So let's see if we can rationalize. So the square root of 3x plus 1 plus 2, multiply that, the numerator and denominator. All right, so the top will have 3x plus 1, and then we'll have minus 4 all over x minus 1 times square root of 3 plus 1 plus 2. Can simplify that numerator. So I have the limit as x goes to 1 for 3x minus 3 all over x minus 1 times 3x plus 1 plus 2. Now remember, we wanted a factor to cancel out. So I think I can factor the numerator and factor out a 3 and be left with x minus 1. So I can cancel that factor out. So I'm left with the limit as x goes to 1 for 3 over this denominator. Then I can do a direct substitution. It's going to give me 2 plus 2 is 4. So I get a derivative of 3/4. Let's try again with another function. Okay. So we have the limit as x approaches a, which in this case is 3. Then we have the function 2 over x minus, if I substitute 3 in, so that's going to give me 2/3 all over x minus 3. Now if I try a direct substitution for this limit, I'm going to get a 0 as a denominator, which is what I don't want. So let's try and combine this fraction into 1. So the common denominator is going to be 3x. That first fraction is missing a factor of 3. So 3 times 2 is 6. And the second one is missing a factor of x. So that's going to be minus 2x. And then that's all over x minus 3. And then remember, I like to make this fraction over a fraction. And you should be yelling at me because I forgot to carry over my limit notation. Okay, then I can do my big C over little c. So limit as x goes to 3, big C is 6 minus 2x times 1. I'm going to go ahead and factor out a negative 2, and you'll see why. So I'm left with negative 3 plus x. And then in the denominator, I've got 3x times x minus 3. I went ahead and did that because negative 3 plus x is the same as x minus 3, so I can cancel that out. So the limit as x goes to 3 is now negative 2 over 3x, and I can do a direct substitution. So negative 2 and 3 times 3 is 9. All right. Now let's do it for any a value. Okay. So we have the limit as h goes to 0 of f of a plus h. So 2 over a plus h minus f of a, so 2 over a all over h. Let's get those into one fraction. So the common denominator is going to be a times a plus h. First one is missing a factor of a. The second one is missing a factor of a plus h. So minus 2a minus 2h. I'm going to make that a fraction over a fraction to do big C over little c. Those two a's can actually cancel out. So I'm actually left with just negative 2h times 1 over a times h times a plus h. Then I have a factor of h that will cancel out. So the limit as h goes to 0 is now negative 2 over a times a plus h. And then I can do a direct substitution of 0 in to be left with 2 over a times a, which is a squared. All right, and that's all for the start of derivatives here. So if you have any questions, let me know.